Well, hey there, I'm Rob. Today we're going to discuss one method of solving a nonlinear circuit component discretely.
The Resistor Companion Method!
So why do we linearize components? Well, we linearize components because computers aren't very good at doing nonlinear math. In order to better calculate the state of an electrical circuit, we need to reduce calculation times, and this is one method used. By linearizing these nonlinear components, we introduce error between what the real value is and the calculated value. Stability is a relationship with how small these calculation error is during the calculations. We will only cover linearization of an inductor using Eulers approximations, but the methods taught today can be implemented for any nonlinear component or approximation. This specific method expresses the nonlinear component as resistance and current source in terms of our current calculation time and our next calculation time t plus 1. So grab a pen and paper and let's begin.
On the left we have our inductor, voltage V of L, current I of L, and the inductance L. This can be expressed mathematically as L di dt equals V of t. We will rewrite this as L di equals V of t dt. This can be expressed as the integral from t to t plus delta t of L di equaling the integral of t to t plus delta t V of t dt. We can evaluate this integral using Euler's forward approximation by assuming that the value of t to time t plus delta t is constant. With this assumption, we can calculate the approximate value of this curve over this time length. By using the value at t times the length delta t, we have our approximation for the Euler forward method of the integral from t to t plus delta t. This gives us the equation L times I of L of t plus 1 minus I of L of t equals V of L of t times delta t. This can be rewritten in terms of IL of t plus 1 as IL of t plus 1 equals VL of t times delta t over L plus IL of t. We can then take this equation and rewrite it as an equivalent circuit, with I of L of t plus 1 going into the circuit, AL of t as the current source in the circuit, and VL of t plus 1 as the voltage over that circuit. Since the Euler forward approximation does not use V of L of t plus 1 in its calculation, we represent it as the voltage over an open circuit. Evaluating this integral using Euler's backwards approximation, we take the value at time t plus delta t and assume that the value holds constant over the entire duration of delta t. With the Euler backward approximation, we get the equation L times IL of t plus 1 minus IL of t equals VL of t plus 1 times delta t. We can put this in terms of IL of t plus 1 as IL of t plus 1 equals V of L of t plus 1 times delta t over L plus IL of t. Using this equation, we can create the circuit on the right with IL of t plus 1 flowing into the circuit, AL of t being the amperage source for the circuit, and VL of t plus 1 being the voltage over the circuit. As the Euler backwards approximation does put the circuit in terms of V of L of t plus 1, here we have V of L of t plus 1 expressed over an equivalent resistance for the circuit. We can evaluate this using Euler's trapezoidal approximation. To do this, we would assume that the average value below the curve is the average between the first and last point of measurement on the curve, or the average between the value at t and the value at t plus delta t. This approximation gives us the equation L of I of L of t plus 1 minus I of L of t equals VL of t plus 1 plus VL of t over 2 times delta t, where VL of t plus 1 plus VL of t over 2 is the average of the curve's value over the distance delta t. We can rewrite this in terms of IL of t plus 1 as IL of t plus 1 equals VL of t plus 1 times delta t over 2L plus IL of t plus VL of t times delta t over 2L. Using this equation, we can rewrite the inductor's circuit with IL of t plus 1 going into the circuit, AL of t is the circuit's amperage source, and VL of t plus 1 is the voltage over the circuit. Phasor analysis can be added to this with a small modification. If the time step is smaller than the additional signal information, this analysis can calculate multiple time steps of the faster signal before other slower signals create an impact on the remaining system. This is done by using what are called dynamic phasors, phasors which are slower than our fastest signal. The inclusion of these dynamic phasors will impact the model's accuracy, but allow the calculation of more complex systems than the single system analysis. This is accomplished by adding the dynamic phasor for the voltage component of the circuit. Once the dynamic phasor of the voltage is applied, we can follow the same steps as initially accomplished. The final expression is very similar to the initial solution, where G and A will now include the dynamic phasor components, making them more complex, as the dynamic phasor itself may be a complex variable. Now let's use this information to solve a simple circuit. Hopefully you've been able to follow along so far, but if you haven't, that's alright. Just rewatch the previous sections till it starts to make sense. For our problem, we'll have a parallel IRL circuit with given variables on the right. We can apply what we've learned so far and create the resistor companion equivalent circuit. Since we will make repeated use of two specific equations, I have labeled them 1 and 2, to make it easier to know when we are using which equation. Our first equation is for A of L of K, our current source. I call it A of L because it's the amperage source of our inductance L at time K. A of L of K is equal to I of L of K plus delta T over 2 times L times V of L of K. Our second equation is the solution to a Kirchhoff current law focused on the top node. We have the amperage for our resistive components in terms of the voltage to the bottom of the circuit, which is in terms of V of K plus 1, and the right side of the equation is the amperage sources themselves. This gives us the equation of V of K plus 1 times the quantity 1 over R plus delta T over 2 times L times V of L of K plus 1 equals I minus A of L of K. In order to solve our two main equations, we need to know what V of L at time 0 is. Since we have no current through the inductor at time 0, we know that V of L is I times R, which gives us 0.2 ohms times 10 amps, which equals 2 volts. Since all of the components in this exercise are in parallel, we'll be using V of L and V interchangeably. Please be careful not to do this when solving the circuit that's more complicated than this example. With this voltage, we can solve equation 1 for K equals 0, giving us 0.05 ohms times 2 volts plus I of L of 0, which equals 0.1 amp. With our value for A of L of 0 calculated, we can solve the equation 2 for V of K plus 1, giving us 1 over 0.2 ohms plus 1 over 20 ohms times V of K plus 1, equaling 10 minus 0.1 amps. We can then calculate the value for V of K plus 1 at K equals 0 to be 1.96 volts. Now take a second and review your work so far. We just calculated all of the component states for time 0. We will now move forward and calculate the states for our first time step of K equals 1. Using equation 1 for K equals 1, we can see that we know V of L of 1 and I of L of 1. Using Kirchhoff's current law again, we can see that I of L of 1 equals the voltage over R of L plus the current source A of L at K, which equals 0. This gives us 1 over 20 ohms times 1.960 volts plus 0.1 amps, which equals 1.98 amps. With our new calculation of I of L, we can solve for A of L of 1, giving us 1.9 amps plus 1 over 20 ohms times 1.96 volts, which equals 0.296 amps. Using this equation 2 again, we can calculate V of K plus 1 for K equals 1, giving us a value of K at our second time step. This value of V of 2 is 1.92 volts. The calculation of every time step will follow the same pattern, which is why this method is so easy to automate.
And that's it. Thank you for watching, and feel free to share what you've learned.